take some minutes first to briefly introduce Xomnia and who we are. So Xomnia is an AI consulting company based in Amsterdam. It's growing by the year. So it's 75 professionals. I think maybe we're a bit bigger than that right now. We span across four main pillars of activity. The projects that we take a project and we implement it as a team, as a Xomnia team. Consultancy, where we are assigned to client as a data science or data engineering consultant, and we integrate with existing teams there. The machine learning engineering traineeship, which feels a need in the market to have people as juniors, but with a little bit more experience than a plain starter. And we also have a fully tailored training program during the traineeship for the juniors to learn and develop themselves. The Xomnia Academy, which provides training to various clients. And on the bottom left, you can see a variety of clients that we have in many industry sectors. And next to that, we also have some side activities. For example, Xomnia Ventures, which is a very interesting a project that we started with a self-driving boat, became a fully fledged company nowadays, the shipping technology. And other initiatives such as Xomnia Sustain, which is a partnership with Ocean Cleanup, providing machine learning and engineering knowledge to them to make our oceans and the environment in general better. So today's program, I think it's a very interesting one from some talks I had with people while preparing it, and for me as well, from personal experience. So I would like to welcome Jean-Yves. He's a CEO and co-founder of Data Mechanics. Their product is a platform where Spark runs on Kubernetes, and it's more like a service, so managed. And I think it's a really interesting topic because it combines two worlds that we know in the engineering space and the data science space has given a lot of improvement. First is Spark for big data processing, and the combination with Kubernetes for proper isolation, containerization, and all the other advantages that you have with Kubernetes. So I think it's a really promising one, and I'm really looking forward to the talk. Regarding the schedule a little bit, we will do, Jean-Yves will take the floor and present his work. And we will try to leave the questions for later. So we'll do a Q&A after the talk and possibly the demo. So if you have a question, maybe you can write it in the chat and we can take it over in the Q&A, or yeah, you can just ask it during that one. So yeah, Jean-Yves, welcome. Thanks a lot for being here. I think it's very interesting talk that you have prepared for us. And yeah, the floor is yours.
Thanks a lot, Sivos.
Stop sharing my screen so that you can take it over.
Good. Okay, so yeah, welcome everyone. Thank you for attending this meetup. I see, yeah, 39 people. That's a great turnout. So yeah, today's meetup is about successes and challenges running Spark on Kubernetes at scale, because that's what we do at Data Mechanics. A few words, just about me. I used to work as an engineer at Databricks, so I studied software engineer, and I worked in the US while it was still a startup. Yeah, I was leading their Spark infrastructure team then. And now, yeah, for the past 3 years, I've been working on Data Mechanics. And when I'm not working, I like to do some trail running in the mountain. In this talk, I'm really going to try to dive in on the technical aspect of running Spark on Kubernetes. I intend not to make it too much of selling our platform, though I think, every now and then I'll talk about how we do things with our platform, because that's where my experience comes from. And so So just a few words about data mechanics. We are Y Combinator-backed startup. We're based out of Europe, but we work with customers globally. And our goal is to make Spark more developer-friendly and more cost-effective than alternatives. And right now, most of our customers use us for data engineering use cases. So, they have some ETL pipelines that they want to run reliably, in a cost-effective way, and have a better developer experience while doing that. So the agendas for today's talk, I'm going to first give a quick introduction about Spark on Kubernetes. Okay, what does it really mean to deploy Spark on Kubernetes, and why do more and more companies choose to do it? And then we'll go over successes and challenges that really we faced. And so I'll be telling some personal stories of things we ran into regarding performance, infrastructure management, scalability, monitoring. And then I'll talk a bit about what's going on right now. So Spark 3.1 is going to be released in the next few weeks, and Spark on Kubernetes is going to be officially GA and production ready. So I'll explain what new features we should expect, and if we have a bit of time at the end, I'll give a bit of a live demo to illustrate some of the points we mentioned earlier. So first, before talking about Spark on Kubernetes, maybe just a few words about Spark itself. It's the #1 analytics engine for big data and AI. What makes it popular is that it's fast, right? With Spark, you can process large amounts of data really fast because you use multiple machines. It's a distributed language. Second, it's easy, thanks to its high-level API. The Python API is the most used today. I think, most of our customers, 2/3 of the companies using Spark use PySpark, and it's versatile. So you can go all the way from business intelligence, interactive data exploration to pretty advanced machine learning and data science to running ETL pipelines or processing data in real time with streaming. Now, where does Kubernetes fit within Spark? Well, Kubernetes is a new cluster manager, also scheduler for Spark, okay? Because Spark knows how to distribute work, but Spark doesn't know how to manage the machines or the containers on which it runs. It needs a cluster manager for that. Before Kubernetes, the main cluster manager people use is Hadoop YARN. And so Kubernetes is a new option available since Spark 2.3 in 2018, and it's been gaining a lot of steam in the recent years. So what does it look like to run Spark on Kubernetes? Well, as a user, you're going to submit a Spark application. And to do that, you're going to talk directly to the Kubernetes API, Kubernetes master. And then Kubernetes is going to start a driver pod. Basically, a pod is a Docker container on its cluster. And then Spark and Kubernetes are going to be directly talking to each other. So in particular, one cool feature that's possible since Spark 3.0 is that the driver can request executors dynamically at runtime. So, I need more machines, give me more. And then as soon as the executors shows up, it's going to start scheduling tasks on them. And then vice versa, once the executor is not needed, it's going to remove it. Earlier in the slide before, I mentioned Spark Submit, but actually there's another tool to run Spark on Kubernetes called Spark on Kubernetes Operator. It's an open source, open source. It's a work that's been open sourced by Google. It works on any platform, not only GCP. It works obviously on top of on-prem as well. And basically, this is what it looks like. Basically, you can start managing Spark applications like a traditional Kubernetes object. So, if you're familiar with Kubernetes, this is how you define not just Spark applications, but any kind of applications you want to run on Kube. So you can apply a configuration file in YAML where there are some new features or pretty advanced configurations you could do, like config maps, volumes, affinities, and so on. And then there's also tooling to read the logs, to describe the application, to restart it, to schedule it. The only downside is it requires a long-running system pod. So basically, this operator mechanism works by having one pod, one container pretty small, very small overhead for your cluster, and they're going to be that's how you get this feature set. But this being said, I would personally recommend it. Yeah, a lot of companies are using it, and yeah, it's open source. We contribute to it every now and then at Data Mechanics. So now, okay, we understand what is Kubernetes and Spark on Kubernetes. What's the benefit of using Spark on Kubernetes over Yarn? First, the benefits of containerization. So on Kubernetes, your application are natively packaged running in a Docker image, and you have control over this image, which means you can package your dependencies like your Python libraries or your complex C libraries and so on in the image, and you build it once, and then it can run everywhere, and there will be no slight environment change between I don't know, your dev environment and production, because everything is in the image and you have control over it. Also, it's pretty lightweight and fast to start up. Okay, you don't need to run I don't know, init scripts, bash scripts, bootstrap actions. And your iteration cycle as a developer can be fast. You can, make a change in your IDE and then Docker build, Docker run, even in the cloud, and have the result in 30 seconds. I'll show you this in the demo. The other benefit is the fact that the Kubernetes cluster, you have a single Kubernetes cluster that you can share for all your Spark apps or also for non-Spark apps. While typically on Yarn, you will often have multiple Yarn clusters, because actually on Kubernetes, each Spark application can have its own Spark version, can have its own Docker image, while on Yarn you have a global Spark version, and you have some you can have some dependencies conflict. And then, why do we care to have a shared infrastructure? Well, because there's going to be instance reuse. So, the same underlying virtual machine that one Spark app was using, the containers we're using, if the Spark app finishes in 10 seconds, the container is gone, and then this makes room for other application which can grab it also really quickly, typically at 10, 20 seconds. So really fast startup time. And then another reason why the startup time is faster is just that there isn't the Yarn overhead. So you don't need to install Yarn on your nodes and Hadoop and so on. So in some sense, if you're more used to the Yarn world, on Yarn, very often there's a question of, oh, do I want a shared cluster and then I run many applications against it, or do I want to have transient, short-running Yarn cluster where I have one Yarn for each app? And there's a trade-off to make, but with Spark on Kubernetes, you kind of get the best of both worlds, in the sense that you have total isolation between concurrent apps, and you have the cost efficiency of a shared infrastructure. The last benefit of Kubernetes is just that it's a very common tool, really popular, and so there's a big ecosystem of CI/CD tools, monitoring tools, networking tools, security tools that you could natively integrate with Spark, and also it's a cloud provider abstraction. If you architect all your stock to run on top of Kubernetes, it'll be easier. It will not be, it still work to move from one cloud provider to the next, but it'll be much easier. At Data Mechanics, we use Kubernetes everywhere, and we were able to build our platform on the 3 cloud provider from the beginning. While if you look at Databricks, which didn't run on Kubernetes, it took them years to go to Azure, and now they are also available on GCP. So now let's talk a bit about some of the successes and challenges that we run into while running Spark on Kubernetes, because this project is pretty new. Now it's starting to be mature, but yeah, there were some difficult days. So the first one, and this is more of a mistake you make as you get started, but yeah, it's something to be aware of. It's basically that if, let's say, you provision your Kubernetes cluster with nodes that have 4 CPUs, okay? So let's say an M5 X large instance on Amazon. And then you're just going to submit a Spark app with the config Spark executor cores equals 4. So tell each Spark executor to have 4 cores. Well, you expect it's going to work, but no. Your executors will be stuck in a pending state. And why is that? Because there's actually a little bit of capacity that's reserved for Kubernetes, and also a little bit of capacity that may be reserved for daemon sets, which is a Kubernetes abstraction that you may define or not. But anyway, you need to be aware of that, and as a result, not give the full 4 CPUs, but 3.6 in this case. This is something that we automate in our platform to optimize basically bin packing, because if you make some mistakes and if you don't pay attention to the amount of CPU and memory that you give, you may end up wasting a lot of space, and so increasing your costs and also running into memory issues and so on. A second, important performance tip is shuffle. How to make shuffle performance. So shuffle in Spark is when Spark executors need to move the data around. And that's very common whenever you do an aggregation by a key, which is different from the key that your data was initially partitioned with. You need to do a shuffle. And this is expensive. You're moving the entire data. So the tip for Kubernetes is to use local SSDs whenever it's possible. So I think on each cloud provider it's possible. On GCP it's a toggle. On Amazon you need to add a D to your instance type, or to use i3 or i4. And then there's a little gotcha. I'll send the slides, by the way, afterwards, and there are some links to some blog posts. But yeah, there's a little gotcha where it's not enough to just configure, choose the right instance type. You need to configure Spark the right way so that it can use the SSD. And the benefit of using local SSD is huge, up to 10x performance gain on workloads that we're suffering, from that we're producing a lot of shuffle. If you don't produce a lot of shuffle, it's not necessary. This is another performance issue we figured out recently with a customer. Slow environment variable lookup. The way Kubernetes works is it defines a lot of environment variables for each Spark application. And curiously, by default, these environment variables are not just visible within the Spark app, but to all the Spark apps that you run, and they kind of accumulate over time. And so as a result, you may have potentially hundreds or thousands of environment variables, and that should be fine, right? But the way Spark looks up environment variables was very inefficient, and a bug was fixed with Spark open source. It's fixed in master, but there is no release yet that has it. It will be in the upcoming 3.0.2 or 3.1. And I just mentioned it because we had some customer jobs where 90% of the time was spent looking up environment variables, which is kind of ridiculous. So we actually implemented a workaround on our platform while we're waiting for the proper fix to be released in open source. Let's talk a bit about infrastructure management. So how do you manage the Kubernetes cluster? And the number of containers to give to your Spark apps. So one feature that's available since Spark 3.0 and very important is dynamic allocation. What that means is that's what I said earlier. The Spark driver can, instead of saying, oh, I want a fixed number of executors, I want 10, you can say, oh, I want the number of executors to go between 0 and 100. And then it's the Spark driver that will dynamically say, oh, I need more executors because I have work to give to them, or, oh, I don't need them anymore, and release them. So this is super important. You need to turn these two config flags. This one is the normal one, and the second one, it's basically shuffle tracking. It's a bit of a limitation of how dynamic allocation works on Kubernetes, is you have to track which executor is storing shuffle files so as not to kill it. Otherwise, you lose the shuffle file that may be needed downstream. So in fact, there's in in Spark 3.1, this limitation will be removed because I'll tell you about it later, but there'll be a mechanism to move shuffle files around. But really, dynamic allocation is super important, particularly if you're doing interactive work. You know, if you're using notebooks, it's the only way to make notebook cost efficient. Second, yeah, in infrastructure management challenge we ran into is to define multiple node pools. So what is a node pool? It's basically a group of nodes that Kubernetes can decide to scale up and down. Each node pool is defined by an amount of memory and CPU. Here you can see an example of what your kube cluster could look like. So you may have one node pool with M5X large on-demand instances and put Spark drivers there. And then you could have other node pools which are all on spot and where you can put executors. And then, yeah, it's up to you to specify the right configurations to say you want the driver to be on demand and the executors on spot, and which type of instance each executor and can use. We make that pretty easy with data mechanics. If you do it the full open source way, it can be some work to set up. And the other thing that's not free is you want to make sure that your node pools auto scale and that they auto scale down to 0. And yeah, depending on the cloud provider you're on, it takes a bit of work. Again, I'll send the slides, and you'll have some follow-up links. But typically, how we do it on Amazon, for example, is we use an open source project called Cluster Autoscaler, and we tag node pools. So really, the VMs with certain label to say if they're spot or not, if they're what's their instance type, and then we have a mapping between these tags and the Spark app configuration to say, oh, I want this executor to only use R5X large instances, or I want the driver to be on demand, and so on. I hope this makes sense. So now, yeah, moving on to another, success, or, well, challenges then success that we faced in terms of scalability. So this is something we ran into with a customer. This was a customer who would, during the night, run a lot of spot VMs. So ask a lot of spot VMs from Amazon, about, between 5,000 and 10,000 spot cores. And yeah, Amazon didn't always have the capacity, so sometimes they couldn't give all the required instances, or the instances would come up, but then you would get spot kills soon after, and so it was kind of inefficient. So there are a few solutions. Which one is best depends on your use case. One is to spread the work across node pools. So instead of saying, oh, I just want i3x large instance, you could say, oh, I want instance of the i3 family. There are ways to do that using the cluster autoscaler project. And then you could, based on availability, or maybe even just randomly launch some instances with x large, some instances with 2x large, some instances with 4x large, and so on. Another pretty interesting and solution is to randomly pick an availability zone for each Spark app. So an availability zone, that's the word they use, at least on Amazon, but I think each cloud provider has that. Physically, they're actually different data centers, and so it's a different spot market. So that's why it's, instead of asking 10,000 cores on one AZ, it's better to ask 3,000 on 3 different AZs. But one thing you have to pay attention to is make sure for one Spark app at a time, the executors should not be spread across AZs. Doing that is a good idea if you just want to build a highly available backend for a web service, but for Spark, that's not good, because the executors, they're going to talk to each other, they're going to send data across AZ, and that's inefficient, and that's also something that Amazon will charge you for. So you can select random AZ, but within the Spark app, all the executors, all the containers should be in the same AZ. And yeah, one last solution. I know at least Amazon EKS lets you do that, is you could define a node pool that's actually backed by different instance types, as long as the instance type have the same amount of CPU and memory. So for example, C5 large, C4 large, C3 large, they have the same memory CPU settings. Just C5 is a newer generation. And then, if for some reason you don't have as many C5 available, EKS will automatically, balance the load and actually give you C4 or maybe C3. Yeah, another scalability issue we ran into recently is we wanted to guarantee a certain application startup time. We wanted to make sure Spark apps come up quickly. And the problem is that if you have room on your cluster, then yeah, usually it starts quickly. If, however, you don't have sufficient capacity, then you're going to need to request a new node from the cloud provider, and that's going to take at least 1 or 2 minutes. So how do we solve this? Two areas. One of them is, maybe actually not all Spark apps need to come up quickly. There were two categories, some higher priority and some that are not really time sensitive. And so one solution is to allow the high priority apps to evict an executor pod from low priority apps. So by evict, really, I mean kill it and take the space that has been freed up. And so obviously the low priority app will have some lost work and will take a bit more time to run. But then that's your goal, is to guarantee fast startup for the high priority one. Or an alternative is to enable what we call over provisioning. So instead of having always the minimal number of nodes necessary for your cluster, we could always have at least one empty node. So obviously this will cost you money, because you need to pay the cloud provider costs for that. But usually, just say one node will make a big difference in terms of your startup time experience. But if you look at the cost of one node for a month, it's about $100 for a four CPU core, even cheaper if you're on spot. So maybe to dive a little deeper with over provisioning. So how do we do that? Because actually Kubernetes doesn't provide this really as a base functionality, but we do at Data Mechanics. The way we do this is we define what are called pause pods. So basically it is a pod for Kubernetes, but it's a pod that does nothing. It just sleeps. And it's a pod with a low priority. So what this means is that when, let's say, the driver requests a new executor due to dynamic allocation, well, because it has a higher priority, it's going to evict the pause pod. But then the pause pod, even though it has a low priority, it still needs to run. And so Kubernetes is going to say, oh, I need a new node to run the pause pod. And so that's where it's going to request a new node from the cloud provider and start the pause pod again. So as you can see, it's it's a great way to guarantee higher better startup time at a lower cost. Maybe last story about successes and challenges, and let's talk about monitoring. So one tool you can use when you use Spark on Kubernetes is the general purpose monitoring tool of Kubernetes. For example, the Kubernetes dashboard is pretty popular. This is this is the screenshot. Or on GKE, they basically have this similar information already. GKE is the Kubernetes from GCP, and it's already available. It's pretty nice. The only downside is that this is a general purpose tool. It does not understand what Spark is. It will just you'll need to dive in and figure out which pod is a driver, which pod is the executor. If you have a lot of executors, it can be hard to figure out to get the right level of information. And also it's hard to reconcile this graph with what happens in your Spark application, because you just see timestamps but that doesn't tell you, oh, this is the big shuffle, or this is the place where we load the data at the beginning of the job, and this is where we write the data. So this is kind of hard to do. You'll need to proceed by timestamp, and it's difficult. So obviously the other tool is the Spark UI. For live applications, the Spark UI is just accessible on the Spark driver, and so you can use Kubernetes port forward to open it. On our platform, obviously, it's just a click. We do that for you. And then for past applications, you have the Spark History Server. And if you want to, if you run Spark on Kubernetes open source and you want to build the Spark History Server, what you will need to do is you'll need to persist the Spark event logs to a persistent storage like S3, and then install the Spark History Server as a Helm chart. It's a decent amount of work also because the Spark History Server is a very unstable beast. And so as a result, we actually developed a free hosted Spark History Server. It's partly open source. Basically, there would be an agent running in your Spark application that's open source, and then it's all hosted for free on our website. So feel free to use that. By the way, this solution that we call Delight doesn't just work on top of Kubernetes, but it works on top of any Spark platform. So if you don't have an easy access to the Spark History Server, you could check out Delight, and it will work for you. And why are we doing this? Well, because actually we want to invest a lot more in observability. Our goal with Delight is to build kind of a better Spark UI that shows you obviously the Spark jobs, stages, tasks, so that you understand what happens on the Spark side, but that also shows you the system metrics, memory metrics, CPU metrics. And our goal with this project is that in a few seconds, when you open up the first page of an app, you see, oh, this job, this stage is the bottleneck of my application, and if I want to improve performance, or if I have stability issues, this is what I should focus on. So right now, this screenshot, animated GIF is not released. What is released is just the free hosted Spark History Server, but we're pretty close to actually releasing it. We will first release it to our customers, but then we actually plan to make this available cross-platform. So you could use this on top of EMR, on top of Databricks, on top of Dataproc, on top of even your on-premise infrastructure. Great. So let me just check what I'm doing on timing. Okay. So I want to say a few words about Spark on Kubernetes being generally available with Spark 3.1, and then I'll try to leave a few minutes for the live demo. So first, let's look at a timeline of Spark on Kubernetes improvements. In February 2018, Spark 2.3, this was the initial release. It was really, it wasn't stable yet. A lot of fixes coming in 2.4, and as well some features that were super important, like volume mounts, how to attach disks to Spark. But Spark 3.0 in June, here they had a year and a half to make more improvements. Had huge fixes, including dynamic allocation. So if you want to start using Spark on Kubernetes, please at least start with 3.0. It's really beneficial. And in the next version, that's really coming up in the next weeks. Right now, the Spark community PMC, they're doing kind of internal testing, but we're really close to a release. Spark on Kubernetes will be officially GA. So today in the doc it's marked as experimental, but now it'll be GA. And yeah, there's been a lot of bug fixes, and there are a few features, and in particular one feature that I'd like to focus on. It's called better handling for node shutdown. And what this means is that Spark will now be able to move shuffle data and cache data during graceful decommission of a node. So what does that mean? That means if, let's say you're using a spot node and you're getting a spot kill, so this node is going away. Well, actually, the cloud providers, they all give you a small termination notice, a minute early or 2 minutes early, they warn you. And here you need to install what's called a node termination handler, and each cloud provider has their own. It's a little daemon set. It's going to be running here, and it's going to be listening, for this warning. And when it knows about it, it notifies Spark, and then Spark is going to stop scheduling task first, because it knows that this executor is going away. And it's going to move the shuffle and cache data to another executor who's staying alive. And so really what this means is that the node is going away and your Spark application continues almost unimpacted. While previously, this data wasn't copied, and so you would lose the shuffle file, and then in a later stage, if they're needed, Spark had to recompute the previous stage to to recover the missing data. So really, it's a huge stability fix. It will make the use of Spot better. It will also improve dynamic allocation, because I said earlier that we had to track shuffle files during dynamic allocation, but here we will just move them as an executor becomes needed. And so really, this is a feature that makes Spark on Kubernetes a lot better than what's on Yarn, and it kind of realizes the dream. I mean, the mission, the goal of disaggregating, separating compute resources from storage resources. Cool. I think I'm done with kind of the slides, and now I wanted to give you a quick demo where I can illustrate a couple points that we mentioned for Spark on Kubernetes. This is the scary part for me, where anything can go wrong. Before I do the demo, just so you understand what's going on, what is the architecture of data mechanics? So when a customer wants to work with us, let's say they're on Amazon or GCP or Azure, but let's say Amazon, they're going to give us an iron role, a set of permission to create and manage a EKS cluster for them. So they don't need to have Kubernetes expertise. They just give us this iron role, and we use it to create and manage the kube cluster. By manage, we mean that, we maintain it, keep it up to date. We scale it also on demand. However, it's in the customer's cloud account, so you have some flexibility. You could connect to the cluster. You could build some pretty complex integrations. And then, we have a notebook handler, so you can use Jupyter with Spark. We have a REST API that you can call from anywhere. If you're using Airflow as a scheduler, we have a data mechanics operator. And as you submit application, it hits the gateway, which is basically our small service running there all the time. And then the gateway is going to actually launch the Spark containers, configure them, collect their logs, and give you access to a monitoring UI. So that's what I want to show in the demo. I'll first connect a Jupyter notebook and show you how to use Spark interactively. And then I'll submit some applications from Airflow. And if I have time, I'll also show you what it's like to build a Docker image and run it. So Jupyter notebooks first. So let me start a Jupyter notebook on my laptop from the command line here. And if you look at the command, it looks like I'm starting the notebook on my laptop, but then there is this parameter, gateway URL, and this tells Jupyter that I don't want to run the commands locally. I want to submit them to the data mechanics gateway. So when I run this opens up the traditional Jupyter interface, and the files here are really local files on my laptop. I would need to use GitHub to manage them. But when I open up a notebook, automatically it's going to start the Spark application on data mechanics. So let me log in and show you that. So this is our dashboard, and we can see the notebook, which is pending here. As soon as the notebook is running, here we go, it means we can actually start executing the code. So let me run this notebook, and in this notebook, I'm installing some libraries, I'm reading in some data, I'm doing some SQL queries, and I'm doing some plots. So let's go back to the UI and see what's happening. While it started running, I think initially the number of cores here should have been 0, but it looks like the notebook already started scaling up. So this is dynamic allocation in action. Probably later, oh yeah, here we go. We just see this number jump to 6. So this is what I told you earlier. The driver requests some executors, it gets them, And then vice versa, once the notebook will be done running, we'll see the number of cores go down to 0. So as you can see here, you can see the full application configuration. Here you can see the Spark driver logs, which are streamed. And here you have access to the Spark UI. And so under the hood, this is just how I told you. We just redirect you to the Spark UI served live by the driver. And yeah, basically that's it for notebooks. I think while the notebook is running, I could show you quickly the Airflow integration. So here I have a little Airflow running. This is actually not hosted by Data Mechanics. Like Airflow, is not fully integrated. Usually our customers already have either Airflow or some other scheduler. If they don't, we could run Airflow, for them, or we could help them basically run Airflow on the same kube cluster. If we look at this Airflow code, we can see the data mechanics operator I was mentioning earlier. And so, yeah, this is how you could basically schedule Spark pipelines from Airflow. And if you look at the API, it's pretty readable. So you'd say, oh, I have a PySpark application. Here, you could put a Docker image that you want to run. I'll show you, I'll tell you more about that later. You could say, well, what is your main application file? You could put in Spark configs. Like, for example, this is a Spark config that disables dynamic allocation. And here I say I want just one executor instance. So basically, this will just use a fixed number of executor, 1. And here I have a little Scala app, and it works really the same way. And now if I trigger this, and if I go to graph view, we should see first 2 parallel applications be scheduled. And then once these 2 parallel applications are scheduled, we run this one in the middle. Let's refresh. Yeah, it says it started them. So if we look again here, we should soon see the 2 Spark apps appear as they are scheduled from Airflow. Here we go. They're pending. So earlier you saw that the notebook started really quickly, like in 10 seconds. That's thanks to over provisioning. We had an instance that was ready. But here, I presume we probably don't have enough instance to start both of them immediately. I could actually check this in the Kubernetes log. Yeah. Maybe it can. Maybe it will actually. So yeah, if you need to get a new node from the cloud provider, typically it takes another minute, maybe 2 minutes, maybe 3. It kind of depends on the cloud provider and the region. This demo is running on GCP, and honestly, GKE is pretty fast. So now actually we can see it's running, and while I was talking, the notebook scaled down to 0 CPU. Why? Because probably the notebook is done. Yeah, it's done doing its compute, and so automatically the scale down happened, and now the notebook has just a driver. And the great thing that happened is that the room that was left out by the notebook executors that were unneeded, it was grabbed by these 2 parallel applications. So again, this is just an illustration of like the cost efficiency of having a shared infrastructure. Yeah, maybe 2 more minutes. I could just quickly show you a workflow of working with Docker. So so here I have a little PySpark project locally. Very simple one, nothing really interesting. But let me make a little code change. Here we go. So in this PySpark project, I import some libraries that I've defined in a company module here. I also have a requirements file where I could put a list of libraries that I want to install with pip. And then I have a Docker file where on the first line, I just say that I'm going to start from a base image published, maintained by Data Mechanics. It's a Spark 3.0 image. And then I'm going to pip install my requirements, and I'm going to copy my code in the Docker image. And I could do more fancy stuff, but just that is pretty cool. And here I have a little script that is going to build a Docker image on my laptop, push it to a Docker registry, and then run this on the Data Mechanics cluster. I could also run it locally, in which case it's just Docker run. But here I'm going to do run cluster. And so under the hood, I'm just going to make an API call to Data Mechanics API. And the image is passed as a parameter. And yeah, basically that's it. So let's open up another window, and let's run that. And my goal is to show you that we can go pretty quickly from making a code change to having the app run live. So the first step was building the Docker image. It's already done. Now we're pushing it. And since my code change was small and Docker caches layers, most of the layers already exist. So I'm not pushing gigabytes of data. It's pretty small. I'm just pushing the delta. And now we just made the API call, and we're waiting for the app to start on data mechanics. We can see that the app is submitted and now running. And so here we go. We can see the driver logs. I don't know how long it took, but I don't think, I think it was probably around 30 seconds. So if we go back to the dashboard, yeah, we can see basically ETL daily. This is the app that I just triggered from Docker, and this is the image I was using. Yeah, I think I'm almost done with the timing. One last thing I could show is just a couple of metrics that we show you on the dashboard. So if we look at the two apps that were started from Airflow here, we can see there are a few new columns that started appearing. Basically, these are some stats that we process for each app after the app has run. So how long did it run? What was the CPU uptime? This is a good measure of your costs. The Spark driver logs, they remain available. You can download them. The Spark UI also remains available. And Delight, so as I said, it's not quite released, but maybe let me try. Oof. Okay, so yeah, I'm glad it's working because the engineering team is still working on that. But soon we'll start releasing Delight. Maybe this will not show. Okay, not quite ready yet. But basically, you will have Delight available similarly a minute or two after your app is run, and you'll be able to dive in and understand what was the bottleneck of this app. So here for this app, it looks like most of the time was spent doing I/O. But yeah, it's a very simple app. And the same information, the same metrics could be found here in the jobs UI. So jobs, if you use to Databricks, on Databricks, jobs is basically a scheduler. But on data mechanics, this is not a scheduler. This is just a monitoring view where you could track for, let's say, this ETL pipeline. You could track some metrics over time. So, oh, how much data am I reading? What is the CPU uptime? This is a measure of your costs. What is the duration, etc. And so you could correlate these metrics and find the same information in the table down there. And so you could go back in time and say, oh, 10 days ago, I ran this app and look at the configuration that was used at the time and so on. Great. I think it's a good time to stop and take questions. Thank you all for listening. I hope this was useful.